Hi, welcome to Pathways to Chemistry. This is Dr. O'Connor. Here we're asked to calculate the equilibrium concentrations of nitrogen, oxygen, and nitrogen monoxide if 0.15 moles of oxygen is mixed with 0.2 moles of nitrogen in a 1 liter container. We're given the equilibrium constant at 2000 degrees Celsius. Well, what we need to do is set up our equilibrium concentration table. If you don't know how to do that, go ahead and look at my previous videos. So we have initial, change, and equilibrium concentrations. Now remember, we are given the number of moles of oxygen and the number of moles of nitrogen in a 1 liter container. Those have to be converted to molarity, so 0.15 moles over 1 liter is 0.15 molar, and 0.2 moles over 1 liter is equal to 0.2 molar. So we have our concentrations. So we have our initial concentrations. We have 0.2 molar nitrogen, 0.15 molar oxygen, and of course initially there would be no nitrogen monoxide. Now, as the reaction proceeds, the nitrogen is going to decrease by some concentration. We'll call that X. The same for the oxygen. And of course, the nitrogen monoxide is going to increase by some concentration, 2X. Remember, the 2 here, this coefficient has to come down here. So at equilibrium, we have 0.2 minus X, 0.15 minus X, and 2X as far as our concentrations. So now we can go ahead and write our equilibrium constant expression. And we have Kc, which is equal to 4.1 times 10 to the negative 4. And we'll set that equal to our nitrogen monoxide concentration. That's squared. Remember, the coefficient becomes the exponent, and of course times the reactant concentrations at equilibrium. So let's go ahead and fill those concentrations in. We have 4.0 times 10 to the negative 4, and that's going to be equal to 2X for the nitrogen monoxide. Again, don't forget the exponent, and that's going to be the concentration of nitrogen, so 0.2 minus X, and then for the oxygen it's 0.15 minus X. So what we need to do is solve this equation for X, and we might have to use the quadratic formula in order to do that. So what I'm going to do is make an assumption here, and I'm going to assume that 0.2 minus X is approximately equal to 0.2. Now I look at my equilibrium constant. I have 10 to the negative 4. This assumption might hold, so we're not going to have too much nitrogen monoxide in the reaction vessel, but you know, when you get to equilibrium constants of 10 to the negative 4 or greater, sometimes you might have to go ahead and use the quadratic formula if you end up with an equation like this. I'm going to make the assumptions, and also the 0.15 minus X, again, is not going to affect that concentration. And so we'll go back to this in a second. If the assumption is not valid, then we will need to solve this equation for X using the quadratic formula. So this simplifies our expression quite a bit by using the assumptions. So I have 4.0 times 10 to the negative 4 is equal to 2X quantity squared divided by 0.2 times 0.15. Okay, so let's see what we end up with here. I'm going to solve this for X, And when I do solve this expression for x, I end up with x equal to 1.7536 times 10 to the negative 3 molar. So I can either plug x in and check the assumptions up here, okay, or I can use the 5% rule. I'll show you how to do both in a moment. So let's see, we have 0.2 minus x, which is 1.7536 times 10 to the negative 3 molar. And that works out to be 0.198, which is 0.2 molar. So this assumption checks out. Let's go ahead and look at the other one, 0.15 minus, and you know this is going to work out, 7536 times 10 to the negative 3 molar. And here we get 0.148, and again that's 0.15 molar. So both assumptions here, they check out. That's good. We could have also used the 5% rule. And basically what we would do is we would take our x, so our 1.7536 times 10 to the negative 3 divided by, I'll divide it by the 0.15 because that's the lower concentration, multiply by 100, and if this is less than 5%, that means our assumption was valid. And that gives me 1.2%, and of course 1.2% is less than 5%, so we're okay. Well, now that we have x, we can determine our equilibrium concentrations. Let's start with the equilibrium concentration of nitrogen first. And that is equal to 0.2 minus x. So x again is 1.8 times 10 to the negative 3. And that gives us 0.2 molar. And then, of course, our concentration of oxygen is 0.15 minus 1.8 times 10 to the negative 3, and that gives us 0.15 molar. And our concentration of nitrogen monoxide at equilibrium is equal to 2x, so 2 times 1.8 times 10 to the negative 3. It gives us 3.6 times 10 to the negative 3 molar. So these are our three equilibrium concentrations.